All right, today we're going to be looking at section 4.1, maxima and minima. First, I want to take you through the textbook. I'm just going to show you some highlights and some of the definitions that you need to be familiar with, and then we'll jump into Pearson, my math lab, and do some of the problems. So if you open up the textbook, it starts out giving you a scenario, talking about some of the concepts that we've learned and covered. You have some visual, and it's going to give us a definition of absolute maximum and minimum. So this will be the highest and lowest points on a graph or a set. So it gives us the definition. Some function is defined on some domain. If we have a y value, this f of c, that is greater than all of the other values in that domain, then it's an absolute maximum. And then we have a similar definition for a minimum. If you have some y value that is smaller than all of the other y values in that domain, then that y value is a minimum. It says absolute extreme value. Absolute extreme value is either the absolute maximum or the minimum value. Okay, so then you get to kind of see some illustrations. So we have a parabola. Let's say that our domain is -2 to 2. This point x equals 0, so that would be f of 0, which is equal to 4. This y value, 4, is higher than all of the other y values in this domain, and so it would be an absolute maximum. In this case, if we say the domain is the whole x-axis, there is no minimum because the graph goes down and down and down without bound to infinity, and so therefore it's saying no minimum. Over here, we have a closed domain from 0 to 2. This gives us an absolute highest point at x equals 0, a value of 4. This gives us an absolute minimum, smallest value of y equals 0 when x is 2. When we have an open interval, okay, we are always approaching but never equal to 4, so we don't know what the closest value is. There's no maximum. That we do get a minimum. And then here, when both endpoints are open, we have no absolute maximum or minimum because we don't reach those points. So just some visuals to kind of help you understand. But again, I would definitely recommend you read and kind of go through all of these. Here are some more illustrations of when we have an absolute maximum or minimum. Here, we're showing 2 points that are just, this is just showing you that these are the minimums. These aren't lines of the graph. This dark line is the graph. These gray lines are just kind of pointing to the illustration, not the illustration, the interpretation of what we're seeing. So we got 2 points, one removable point, and we have a fixed point, and then we go to an open point. No maximum, but we do get a minimum. We got 2 different points that are the same for the minimum. Here we have a minimum. This point is not a minimum. It's not the lowest point. This is the lowest point. This would be the highest point, but we don't reach it, so we don't have absolute maximum. We're getting close to that point. All right, so extreme value theorem. We have a function that's continuous on a closed interval. So it's telling you if it's closed, there is an absolute maximum value and an absolute minimum value. So if you have a closed interval, you're guaranteed to have a max and a minimum value. This endpoint is not the minimum. Okay, this lowest point is the minimum. Highest and lowest are the minimum. Sometimes it could be the endpoints, but we will always have one on the closed interval. This one is not closed, not continuous either, so it breaks 2 of those definitions, so we're not guaranteed to get a maximum and minimum. Definitely go back and follow the definition. Function is continuous on a closed interval, so it got to be continuous, one smooth line, no breaks, no jumps, and closed circle endpoints. Give you some explanation here. Then we start talking about a local minimum and maximum. Now, when we talk about a local minimum and maximum, we're really talking about like an interior point, like a valley right here, or like a mountaintop, like a hill, top of a hill. So here is the definition for local maximum and minimum. says suppose C is an interior point. So that means it is not an endpoint. It cannot be on the edge of the domain. It has to be somewhere on the inside. It's an interior point on some interval where the function is defined. If you get a y value that's greater than all the other y values on that interval, then that value is a local maximum. If you have a y value that is lower than all of the other values in that interval, then it is a local minimum. Okay, so here is an example. You have P. This point P would be a minimum. This point Q would be a maximum. R would be a minimum, that little valley. S would be a maximum, a local maximum. Now, as for purposes of this graph, these endpoints would not be a local minimum or maximum. They wouldn't even be the absolute minimum or maximum. Some we will have to calculate. So sometimes you'll be given a graph, some you'll have to calculate. So it talks about critical points when you're trying to find the extreme maxima or minimum, or local maximum or minimum. And so the local extreme value theorem is if it has a maximum or minimum value at C, then the derivative of that value exists, and the derivative is equal to 0. So we'll take the derivative of the function, set it equal to 0, and that will give us critical points to determine if it is either a maximum or minimum. And then another thing, an interior point C in the domain of F is a point at which f prime of C is equal to 0 or f prime of C fails to exist. So this is, again, critical points that's going to show us potential maximum or minimum points. So here's one where they show you we have a minimum at C. F prime of C does not exist, whole. A local minimum. I would think that would be a local maximum, a high point. This one says we have a local maximum at C. FC does not exist because we cannot take the derivative of a corner point. So those are two examples similar. We have a couple more smooth curves. And then here's an example of locating critical points based on the function. You also have a visual. And again, it goes through the process of locating those points. Locate the extreme value interior points. Absolute extreme may also occur at the endpoint, so we're also going to check those. And then we're going to use these two procedures for locating the absolute extreme values of the continuous function on the closed interval. So those are kind of like the steps. Here's the processes listed out again. You see a few examples. I'm going to spend our time doing these examples in my math lab. And then that kind of ends the chapter. So then you got some practice problems in the textbook if you want to go through. But from this point, I'm going to go ahead and switch on over, and we're going to start working some examples.